I will be starting in-person classes here in Asheville, North Carolina soon. If you would like to join and attend an in-person class here in Asheville, North Carolina, please click on the Silicon Dojo meetup link down below. Welcome back. As you know, I am Eli, the computer guy, and in today's class, we're going to do an introduction to TCP IP version 4. Yes, we are going to be talking about TCP IP version 4. So this is the standard networking protocol most of us use in the modern world to allow our computers to be able to communicate with other computers, whether it's on the local network, whether it's out to computers on the internet, whether it's IoT devices, some kind of sensor, that type of thing. Almost all devices in the modern world use TCP IP version 4. It is important to understand that TCP IP version 4 is not the same thing as Ethernet. When we talk about the Ethernet technology, that is a technology for being able to connect computers together at like the very lowest level. What kind of cabling will you use? What kind of jack will you use to be able to connect devices into the network? How will things like switches work? Collision domains, that type of thing. All of that is defined by the Ethernet standard. On top of the Ethernet standard, you then have a networking protocol. Again, a protocol is a language, and so with TCP IP version 4, this is the language that computers will use to communicate with each other over the Ethernet technology. Kind of think about this like having a conversation in the real world over a telephone line, right? The telephone, think of that as that Ethernet technology, and then the language that you use is the protocol. Do you speak in English? Do you speak in German? Do you speak in Chinese? Do you speak in some, coded language or that type of thing? That is the protocol that we're going to be talking about today. Again, when we talk about protocols, there are a lot of different protocols out there. Normally, again, nowadays you'll be dealing with TCP IP version 4. When I started in the tech world, you may get this on a test. I will talk about this because it may be on a test. We had something called IPX SPX, which was a protocol that was used that competed with TCP IP. There was something called NetBEUI. There was something called AppleTalk. Even now, there's something called a TCP IP version 6. And, we're going to be using that next year. That's what my instructor told me back in 2000. I remember back in 2000 when I was sitting there and I had to study this whole book on TCP IP version 4, and my instructor said, well, we're going to be moving to TCP IP version 6 soon, but you will have a legacy equipment using TCP IP version 4, so you're going to have to know this protocol. It's now 2022. We still use TCP IP version 4. TCP IP version 6 is actually used in the real world, just not a whole hell of a lot, or at least where most people will see it. So when we talk about Ethernet and we talk about TCP IP version 4, it is important that you understand these are two entirely different things. You can have different protocols on the Ethernet technology. It's just kind of one of those things. How it all works out, we're just currently using TCP IP version 4. So in the class today, we're going to go through a lot of the basics for TCP IP version 4 so you understand what's going on. And with many things here, you give it a little bit of time, you think about what I'm talking about, and a lot of things are going to become much clearer to you. Okay, so as we dive into the class, I'm going to give you the very first thing to be frustrated over. From the very first moments of this class, you're going to be like, what? Gosh darn it. So one of the important things to understand about TCP IP version 4 is it's not actually a protocol. Whoa, wait, what? Have you been saying TCP IP version 4 is a protocol? What do you mean it's not a protocol? What the hell? Here's the thing. TCP IP version 4 is actually a protocol suite. So it's actually a set of a number of different protocols that have been all packaged together to give us what we call the TCP IP version 4 protocol. And so it is important to understand that because there are some subcomponents, some other protocols that go into this protocol suite. And whenever you're designing your infrastructure or whenever you're maintaining your infrastructure, you might find somebody decided to do some stupid configurations on your infrastructure, and you might run into some problems because TCP/IP seems to be working, except where it isn't. So anyways, when we talk about TCP/IP, right, the first protocols in the TCP/IP version 4 suite is Transmission Control Protocol and Internet Protocol. So what TCP does, right, so this is its own protocol. We talked about this before. There's the TCP three-way handshake. There's this TCP windowing, right? And so what TCP does is this is the protocol that actually allows for the communication between two different computers. So basically, when the computers are talking to each other, there's the three-way handshake that TCP does, where basically you send a SYN signal, and then the second computer sends a SYN acknowledgement back, and then the first computer sends an acknowledgement to that SYN acknowledgement, and that gives us the three-way handshake so that the computers can start communicating with each other. TCP also deals with the windowing. So basically, when the two computers are talking to each other, the first computer starts sending data to the second computer. The second computer says that it's receiving the data, and so then the first computer starts sending more and more and more. We talked about this in a previous video, but basically that's with the TCP windowing. And so what TCP does, TCP is responsible for the actual communication at that transport layer, the level layer 4 on the OSI model between the two computers. What IP does, this is the Internet Protocol. And guess what it does? Guess what? It's called the Internet Protocol. Basically, the Internet Protocol allows us to create our own addresses for computers and then be able to logically separate out networks. Remember, there's something called media access control, or a MAC address, and this is used in switches. So every single device, essentially every single port that's ever been created, has a globally unique identity number, right? Did you hear? Did you hear? They're going to put globally unique identifiers into computers. Yeah, I heard. They started doing that about 50 years ago. Anyways, that's just my own snark. But yeah, so every single network device that you have, there is something called a MAC address. Basically, that MAC address has two components. The first component is the vendor identifier, and then the second component is essentially like a serial number. These two numbers come together, and that gives us our MAC address, our media access control address, and this should be absolutely globally unique. Like when I say globally unique, like literally none of these on the rest of the planet. It's essentially like a fingerprint for the computer. And I'm not joking. They've been on computers for 50 years now. But anyways, this is, though, at the layer 2 of the OSI model, basically where the switch layer is, the data link layer. And so with this, you don't really get any logic for how you create addresses for your computers, and there's no real logic for how you separate out networks, right? It's basically you connect computers to the network, they all have their MAC addresses, and that's it, really. There's not a lot to it, right? So what you do with the IP protocol, the Internet Protocol, is this allows us to assign some kind of address that we've created, some kind of address scheme that we've created, separate out networks, and then have traffic route between those networks based off of those IP addresses, right? So, 192.168.1.2, let's say, that is an IP address, right? If you go out to CNN.com, I don't know, 208.55.66.1, something like that. This is an address that you can manually give to your computers so you can design your infrastructure for how it's supposed to communicate. With the IP, right, this is what is called a routable protocol. And so that's what we talked about before with LANs. So, right, LAN is a local area network. Essentially, more or less, all the computers or devices that are connected to an individual switch, right? That's a LAN. You separate LANs with a router. So the router is what separates different LANs. And so if you want traffic to be able to route from one LAN to another LAN, that's with the Internet Protocol. It basically has configurations in there for routers. There's something called a default gateway. We'll talk about in a little bit. Essentially, you have a computer on one network. It will try to communicate out, see if the IP address it's looking for is on the local network. If not, it will then go to the default gateway, the router that it has configured, and then it will try to see if the computer is on the other side of that router, again with the internet or whatever else, something called the wide area network. So TCP is the communication between the two computers themselves. The Internet Protocol allows us to create this addressing scheme and create more complicated types of infrastructure. So those are the first two of the protocols. The next protocol is ARP, and we have talked about ARP before, and this is the Address Resolution Protocol. And again, it's very important to understand the technology world that is not magic. There has to be a step for everything. It's not like this happens, magic happens. There has to be a step for everything. And so what ARP does, Address Resolution Protocol, is it resolves IP addresses, 192.168.1.10, let's say, to MAC addresses, right? Because remember, all the computers that are connected to a switch, the switch only understands MAC addresses. Switch are on layer 2 of the OSI model, the data link layer. Layer 2 of the OSI model literally does not understand the concept of IP addresses. You give a switch an IP address and the switch goes, oh, right? It doesn't know what to do with it. What it does understand what to do with is something called a MAC address. And so what happens is when you have you have your switch and you have your computers connected to that switch. What's going to happen is, let's say you have the computer up here and it has an IP address of 192.168.1.5. And it's trying to find, let's say, 192.168.1.11, right? So that's a different address. So what's going to happen is if this computer does not know what the MAC address is for the 192.168.111, basically what's going to happen is this computer is going to send communication into the switch, and it's going to essentially say, hey, who is 192.168.111? That communication will go out essentially, more or less, every single port in the switch. And then the computer that is 192.168.111 will say, hey, that's me, and this is my MAC address. Right? So what ARP then does is you have an ARP table in your computer, basically, that resolves IP addresses to MAC addresses in your individual computer, whether it's a Windows computer or whether it's a Mac, Linux, whatever else. Then what's going to happen is when your computer wants to communicate with 192.168.111, it's then going to use that MAC address. Within the switch has an ARP table. Has a MAC address table, and in that MAC address table has all the different MAC addresses with the physical port that MAC address is connected to. So 192.168.1.5 is going to say, hey, I want to communicate with this MAC address. The MAC table in the switch is going to say this MAC address is on port 14. Now, again, we talk about this. This isn't TCP ports. This isn't a different port. It's the actual physical port that's on the switch. And we'll say, okay, that MAC address is connected to port 14. And so then the traffic will be routed to just port 14. It will not go out the other ports on the switch. Because remember, in the Ethernet world, we are in something called a collision domain. Basically, everybody shares the exact same wire. So if people are communicating, or computers are communicating on the exact same wire at the same time, there will be a collision that causes a disaster. So what switches do is it routes the communication only to the ports where the MAC address is. And so that's ARP, that's Address Resolution Protocol, which is part of the TCP IP suite. Then past that, we have ICMP. And this is the one that can cause you trouble when you start having your interns pretend like they're security experts on your network. So what ICMP is, it's the Internet Control Message protocol. And basically, this is a protocol that allows you to troubleshoot your network. Normally, with this protocol, you use the tool ping is a tool for ICMP, or something called trace route. So what ping does is, let's say I just want to see if a computer is on the network. Again, when we think about the OSI model, right, the 7 layers of the OSI model, if I am not getting a response from a server, maybe for any number of reasons on the different layers of the OSI model. It may mean that the server is disconnected from the network physically. It might mean the cable for the server is disconnected. It might mean there's something wrong with the TCP IP protocol on the server. There might be a firewall issue on the server. Some software might not be working on the server, the whole 9 yards. And so one of the first things that I'm going to do when I'm troubleshooting and I can't connect to a particular server, and again, this may be a local server such as your email server, or it might be, again, CNN.com or your own web server that's out on the internet. If people are having problems connecting to it, the first thing that I'm going to do is ping. And basically with a ping command, you say ping, and then whatever address you want. You want to ping 192.168.1.1 or whatever, or you can say CNN.com. That uses something called DNS. But basically what the ping command is going to do is it's going to ping and basically say, hey, 192.168.1.1, are you there? And then 192.168.1.1.1 is going to send a response. And then with that, you're going to get some interesting information, such as how long it took to get the response, how often you're getting the response. Again, one of the things to remember in the networking world is when you're doing troubleshooting, a hard fail is the best fail, right? When you go to do a troubleshooting routine and something fails, and it just fails, dead, don't work at all, your life is generally pretty easy. You're going to be able to figure out the problem. And one of the big problems, one of the big issues you can have, though, is when you have quirky fails. So if I ping, right? So if I try to ping a server and I get no response back, that's actually pretty easy to start trying to troubleshoot. Or if I ping a server and I do get a response back, that's pretty easy to troubleshoot. The problem that you get sometimes is with when you're pinging is basically that you'll get responses, and then you won't get responses. And you'll get responses, you won't get responses. You get responses, then you won't get a response. And that can show you where you're having some kind of quirky issue on the network. Generally, maybe the network wasn't built properly. You have some kind of degradation, like you have physical wire connections, that type of thing. So anyways, one of the interesting things with the ping command is that when you use it on Windows, it will ping at least 4 times. So with Windows, it'll ping once, and then you'll get a response. It'll ping again, and you'll get a response. You'll ping again, and you'll get a response. And you ping again, and you get a response. So if you send 4 pings out, you get 4 pings back, 4 responses back, and you get the information. Then you can feel pretty confident. Okay, everything's good. If you're in the Linux world, do be careful. If you're in the Linux world, when you start the ping command, it just starts pinging and it will not stop until you tell it to stop. But if you start pinging, and again, you do get complete responses, that's fine. Or if you don't get any response, actually, again, that's pretty easy for troubleshooting because you know the server or whatever is not in the network. But by doing these multiple pings, basically what you might see is, okay, I ping and I get a response. I ping and it times out. I ping, it times out. I ping, I get a response. Why we do the ping command multiple times is just to verify that we're getting a consistent result, because then if you start getting these inconsistent results, well, you get to have fun with troubleshooting. But basically, ping is part of the ICMP, the Internet Control Message Protocol. Then you have something called traceroute. Traceroute's pretty cool. Essentially, what will happen is that when you run the traceroute command, every single hop your computer makes in order to communicate with the server that you're looking for, you will get a response from essentially all of those different hops so that you can see what's going on. You can actually see how your traffic is being routed to get from your computer to whatever server that you're trying to go for. The issue with ICMP, and again, where ICMP can cause some people some trouble, is this is its own individual protocol. It's part of the protocol suite, but again, it's one of those things that's packaged together. And if you have an intern that's pretending to be a security expert, they might decide to turn ICMP off. So you'll see this. Some people recommend this from a security standpoint. So there is a concern with hackers or folks like that. The first thing that they will do is try to survey your network, try to see all of the different computers and devices that are on your network. And one of the ways they can do that is by doing a ping sweep. Essentially, ping 192.168.1, ping 192.168.2, ping 192.168.3, and all the way up to 254, essentially to see who does respond and who doesn't respond. And so that way they're able to start mapping out your network to understand what your network looks like. And so what some interns think is a really good idea is, oh no, what if a hacker maps my network? What I'm going to do is I'm going to turn off ICMP so that therefore no hacker is going to map my network. Problem is, again, what I'll remind folks is these are just tools. These are just tools. It's kind of like a shovel. It's kind of like a shovel. You can use a shovel to plant flowers, or you could use a shovel to bang your spouse on the back of the head and then bury them out back, right? It's just a tool. Imagine for a second there was a murder in your city or county or whatever else, and so the police decided to ban shovels. Somebody got hit in the head with a shovel and buried in the backyard, so therefore they're going to make sure nobody else gets murdered by getting hit in the head with a shovel and buried in their backyard. Which, theoretically, I guess it makes some kind of logic there. A weird kind of logic. But that's kind of what interns do with ICMP. Because a hacker could survey your network, do a ping sweep of your network, and learn about the devices on your network using ICMP, what they decide to do is basically turn ICMP off so the hackers can't do that. But here's the thing, when you go in to start troubleshooting your network, if you literally don't have the ability to do something as simple as ping, life is going to get really, really, really miserable. Especially, again, with that whole intern scenario. Do you understand one of the most important things if you're going to be a technology professional is standardization, right? Lord help you. Even if you do decide to turn ICMP off, then you basically should turn it off to everybody, right? All workstations should have ICMP turned off because of whatever security policy you've decided to go with. Here's the issue. What happens if the intern doesn't actually touch every single computer, all 200 computers on your network? What if they just go in and they just decide to turn off ICMP on 3 or 4 of those computers? And then a year later, you're trying to troubleshoot what the hell's going on. And you're like, okay, all I'm going to do, I'll just ping the computer, see if it responds. And then you ping, and you don't get the response that you're expecting. And then you get into just absolute troubleshooting misery. So anyways, that's what ICMP is. Again, it's one of the protocols that are part of the TCP/IP version 4 suite. And don't turn it off. Unless you know what you're doing. Unless you can follow everything I'm saying in these videos and point out every place I say something slightly incorrect, please don't turn off ICMP. The final protocol that is part of the TCP/IP4 suite is called IGMP, Internet Group Management Protocol. Essentially, this protocol is used for multicasting, right? So there's a lot of times that when computers are communicating, they have to communicate to multiple computers at once. And so instead of essentially creating direct connections with all of those each individual computers, what one computer can do is it can use the IGMP protocol and essentially send out the exact same communication to all computers at the same time. This is used for broadcasting. When you use ARP, when you're doing that MAC address resolution, use this something called broadcasting that'll send out a communication to essentially all the computers on the local LAN. That would use IGMP. There's some other basic things that you'd use IGMP for. It's not, you don't really screw with this a lot. Again, ARP is TCP is very important. IP is very important. ARP is very important. You need to know that. ICMP, you need to know not to touch it. IGMP, more or less. It's just kind of one of those things that's there, but it allows for essentially TCP/IP to be able to communicate with all the computers on the network for broadcast communications. And again, when you're trying to find a MAC address on the network, that would use IGMP. There's some other things out there where you'd use what's called multicasting, but for the most part, you're not going to mess with that. So that's the basics of the TCP/IP version 4 protocol suite. Do realize with TCP/IP version 4, it's not technically a protocol. It is a protocol suite with TCP, IP, ARP, ICMP, and IGMP as part of it. So now that you understand a little bit about the TCP/IP version 4 protocol suite, it does get a bit difficult to get through this word salad every once in a while. The next thing I want to talk about is the protocols that are built on top of the TCP/IP version 4 protocol suite, right? So TCP/IP version 4, you have TCP, you have IP, you have ARP, you have ICMP, and you have IGMP. That's what makes up the protocol suite. And then, basically on top of that, you have other protocols that you will use in the normal world in order to do certain tasks. Again, a protocol is a language. A language is going to allow you to do certain things. So a protocol that is built on top of the TCP/IP stack is something called HTTP. This is Hypertext Transfer Protocol. So most likely, in order for you to view this particular video, you went to a web page, you're watching this video on a web page, and there's a whole bunch of most likely 50 ads surrounding this particular video. All of those ads are presented to you basically based off of HTTP. This is a protocol essentially for being able to view and to be able to interact with web pages. Most or all of these protocols that are built on top of TCP/IP use something called a port number. Now, it's very important to understand this is not a switch port number. A switch port are the actual ports that are physically on the front of a switch. This is a TCP port. So there's something called a TCP port, and we'll talk about this in a little bit. HTTP uses port 80. So all of these protocols, more or less, use their own individual ports. You have something called FTP. This is called File Transfer Protocol. So if you're going to be uploading or downloading large files on your network, you may use FTP. You also may use something called SMB. That's probably what you normally use. It's called Server Message Blocks. That's something for another class, though. FTP uses TCP port 21. You then have another protocol called SMTP, Simple Mail Transfer Protocol. So when you send or you're receiving emails, there is a protocol that allows computers to understand how that whole email system works. That uses SMTP, and SMTP uses TCP port 25. You then have a SNMP. So SNMP is something called Simple Network Management Protocol, and it's cool. I like me some Simple Network Management Protocol. Again, a lot of the security interns don't like Simple Network Management Protocol because they've never managed networks in their lives. But anyways, this is a particular protocol. What this does is the computers on your network, if you need to be able to view like not just CPU utilization, but CPU heat. What is the heat of the different CPUs and the different servers on your network? What is the heat on the RAM of different servers on your network? All this kind of like really basic, low-level technical information about the servers, you can actually pull all of that in using this SNMP, and it is absolutely fabulous. This is another protocol built on top of TCP/IP. You have RTMP, again, for watching this particular video. This is one of the protocols that's probably being used, called Real-Time Media Protocol. So whenever you're watching video streams, anything like that, most likely you're going to use that protocol. And there's a protocol called SIP if you're doing voice over IP communications. So if you have some Cisco voice over IP phone or a Polycom voice over IP phone, you're probably using SIP as that protocol. And so these are protocols that are built on top of the TCP/IP version 4 stack that allow you to do different things. HTTP allows you to view web pages. FTP allows you to upload or download files. Again, something called SMB, the same thing for dealing with files, only in a bit of a different way. SMTP, again, remember, every single thing that is done on a computer has to be coded, has to be designed, has to have standards, right? So for you to receive emails, there is actually a protocol called SMTP, and this is literally the language for how emails will get routed. Again, simple network management protocol, RTMP, you have SIP, and you just got a whole crap ton of other protocols out there. And so these are some of the protocols to be thinking about. Again, and when you go troubleshooting, you're thinking about that OSI, the OSI model, right? If a network cable is broken, that's layer 1. If there's something wrong with MAC addresses, that's layer 2. That's a switch layer. If your IP addresses aren't working, that's layer 3, right? Something going on with the router. Then you have something going on with TCP, the actual communication between the one computer and the other. That's layer 4. That's up at the transport layer. And so then with these other protocols, with things like encryption, things like compression, that type of deal, that they may be up at higher levels within the OSI model. And so that's where, again, with troubleshooting, like if I ping, right? As long as some intern hasn't been stupid enough to turn off ICMP, if I ping, then I know at least all the way up to layer 3 of the OSI model is working. If I can ping from one computer to another, I know that it's connected. I know that the switch is working, and because I'm pinging, I know that that it's actually routing and the IP level is working. So once I know that, then I can start doing some troubleshooting up to these higher levels. So when we talk about the protocols that are built on top of TCP/IP version 4, this is what we're talking about. So now that you know that TCP/IP version 4 is a protocol suite, and you know about the protocols that are built on top of TCP/IP 4, let's start talking about the actual configurations for when you're configuring your servers and your devices on a TCP/IP version 4 network. So the first thing that I want to talk about is something called the IP address, right? So I just pulled this up. It's a screenshot. So if you look at your network configuration setting on a Windows computer, you should see something that looks like this. And we have a number of different values here, right? We have the IP address, we have the subnet mask, we have a default gateway, we have what's called the primary DNS server, and we have the secondary DNS server. And I want to walk through all of these concepts. The first thing here is the IP address. And so the IP address is something that you are able to configure. Again, a MAC address should be hard-coded at the manufacturer. And to be clear, more or less, you can't change it. You kind of sort of can. Well, let's for now just say you can't, right? That's just configured, at the vendor. You can't change it. The IP address is something that you can change and you can modify at will. And so this is going to be the identifier on the network for your computer or your device. Basically, any IP addressed piece of equipment that you're going to be interacting with needs its own IP address. And so what I talk about with this is to understand a switch, kind of sort of, a switch doesn't really have an IP address. Now to be clear, if it has a web management console that allows you to configure that switch, that is actually kind of sort of like its own server, basically is its own server. So there might be an IP address for the web management console of your switch, but there's not an IP address associated with the actual physical how everything is connected into your switch. So your old switches, back in the day, you would have dumb switches or whatever else. There is no IP address associated with the actual functioning of a switch. Again, that is a layer 2 on the OSI model. That's where MAC addresses are stored. There's no IP address there, except for the management console. But anyways, it's a computer world. If you don't say accept, you're not in the tech world. But basically, when we're talking about this, we're talking about things like shared printers, right? So if you have a networked printer, that will have an IP address. Your computer will have an IP address. Your server will have an IP address. Your router, so your router is a piece of networking equipment that is at layer 3, right? So that's at the internet layer, the IP layer, so that will have an IP address. Your voice over IP phones will have an IP address. Your surveillance cameras may have an IP address, the whole 9 yards. And so all of those have to be configured to be individual on the network. So there should only be one computer with any one specific network on your local area network. If you have two computers on your network that share the exact same IP address, unless you've done it on purpose, and there are reasons to do it on purpose, but unless you've done it on purpose, you will run into problems because essentially when the traffic is looking for a particular IP address, sometimes you'll get the traffic to basically bounce between two different computers. Sometimes the information will be routed to one computer, sometimes it'll get routed to the other, sometimes everything will fail out. It'll be a bit of a disaster. And so with the IP address, there should be only one IP address, unique IP address on the network at one time. Basically with this, when we're talking about IP addresses, the way that I would say this is think about this essentially like a house number, right? Where, you're going down a road and, it's Cortland Avenue or whatever your road is. And this is 20 and this is 21 and this is 22 and this is 24, right? Those are the individual houses or individual buildings on the road. And that's the unique identifier for each one of those computers or each one of those devices. Now, beyond the IP address that needs to be configured to be manually unique on the network, you then have what are called TCP ports, right? So we talked about this with like HTTP. HTTP uses port 80. The way you think about ports when you're thinking about IP addresses is the IP address is the address of the building. The ports are the different suites in the building. Again, think about this with FTP or HTTP or SNMP or whatever else, right? If you go to a building, one office is for a lawyer, one office is for HR, one office is for the IT department, the whole 9 yards, right? So you would go to an office number based off of what service you're trying to get out of that building. That's essentially the same thing we're dealing with TCP ports. So this is where, when you get more into it, you'll see somebody like you're trying to connect to something on the network and it asks you to plug into a port. You might see like 192.168.1.10 and then you'll see port 80. And so what this is saying is I want to connect to this IP address at this particular port, and then it'll drop you in essentially to that door. And if everything's configured right, then whatever you're doing should work. And if it's not configured properly, then it might not work properly. The important thing to understand is that essentially all of these ports should be used for these additional protocols that are on top. And again, one port shouldn't be used for more than one service. So HTTP is going to use port 80. FTP is going to use port 21. SMTP is going to use port 25. And so when you plug in manual configurations, many times it'll say, okay, I need the IP address and I need the port number. What you will do is you will look at the documentation and say, okay, this is the IP address for the server or the device I'm trying to connect to, and for the particular service I'm trying to connect with, this is the particular port number. Now, if you use the standard, protocols, HTTP, FTP, the whole 9 yards, all of these ports are very well documented. Essentially, you just go to Google and see what port they give you, right? I need the SSH port, and they'll give you the SSH port. If you're using proprietary software, especially maybe if you're using like Microsoft, so Microsoft, obviously, they have a lot of server software out there, server services. So those aren't standards. That's not open source software. It might not be as easy to find. mind. If you're trying to connect to a particular server for a particular service, you may have to go and look at their particular documentation to understand what ports you need to connect to. I think about this. I used to sell and deploy something called Small Business Server, which was awesome. If Microsoft ever wants to start selling that product again, I would sell the hell out of that. There's something called Small Business Server. Essentially, think about this. It was an entire enterprise server software suite that was essentially just shoved into one little box. It was an amazing piece of software that you could use for companies with like up to 50 employees. But whenever I configured that, right, there are a whole bunch of different services people would need to connect with. There was a Outlook web access. So, again, we're talking about 2009 here, right? So you wanted your employees to be able to interact with their email accounts without having to use Outlook on their local computer. They could actually go to an IP address that would give them access to something called Outlook Web Access, and then, it looks like Gmail or whatever people are used to using now. Outlook Web Access required a specific port to be open. They had VPN services, routing a remote access server. That's the VPN service for Windows. That required its own port. There are about 10 ports that you had to make sure that were open on the firewall, and you had rules and all that for. And so basically I'd have to go and take a look at the documentation so that I could make sure those ports were configured properly and all the different networking equipment. There's other equipment, though, you may install in the network where it starts to get a little bit more difficult, right? When you're dealing with SMTP and FTP, it's really easy to find the port information. When you're dealing with Microsoft services, it's pretty darn easy to find the information. The thing is, again, remember back in the day, I used to install things like digital surveillance systems. So digital surveillance systems, obviously they allowed you to look at your surveillance system when you were remote. So if you were in Timbuktu and you wanted to look at what was going on in your warehouse, in New York City, you could just open up, a web page or whatever and be able to see what was going on. One of the issues we ran into is that many times that software, the documentation would be piss poor. Piss poor is a very polite way to say it. Basically, sometimes when we got lesser quality equipment, again, cheaper equipment because people wanted a cheaper solution, the documentation was absolute garbage. And so many times it was kind of difficult to figure out what ports these digital surveillance systems actually require to do what they were supposed to do. We ran into this problem, especially with what's called PTZ systems. So PTZ is a pan, tilt, zoom camera. And so you would have port 80 would have to be open in order to be able to view what the camera was seeing. But then to send commands to the camera, that required a different port to be open that may or may not have actually been documented. And so you can run into problems like that. So if you go into a situation where, again, you have surveillance equipment, maybe telephone type equipment, maybe alarm system equipment that's all running over your Ethernet network using TCP/IP4, you may run into issues where you simply don't know what the hell the port number is. One of the other things to realize, again, when you're dealing with ports too, when you're dealing with software, sometimes the software that you're going to be using will actually require a range of ports, right? So it will use between port 6000 to ports 7000 for whatever reason in order to deal with communications and all the different sessions and all that kind of stuff. They will use a range. And so again, this is just something to keep in your mind. Firewalls, and we'll talk about firewalls in a bit, but basically firewalls are specifically used to block ports. So one of the reasons you might get quirky errors is, let's say you need a range of TCP ports open from 6000 to 7000, and for some reason in your firewall, somebody opened 6000 to 6500, but they closed 6500 to 7000. Right? So only half the TCP ports are available. This is one of those times where you might start getting some really stupid errors where sometimes the communication works and sometimes the communication doesn't. And you can run into issues with that. And so basically with these TCP ports, it's all of these protocol suites that are built on top of TCP. They require their own TCP port for whatever software that they're going to be using for whatever types of communication. And so this is just an additional thing to be keeping in mind when you're dealing with TCP/IP and IP addresses. Okay, so now we get to talk about subnet masking. Yay! But I will say, I'm going to wimp out. I'm going to wimp out a little bit today on this particular class, and we are not going to go deep into subnet masking. I do not know what it is with the subnet masking concept. I've been doing this for 20 some odd years. Subnet masking shouldn't be that difficult, but it still kind of makes your brain melt whenever you try to do it. So today, when we talk about subnet masking, we're just going to talk about the general concept of subnet masking at a very simple level. And then in a future class, when I've had a little bit more coffee and a little bit more sleep, then we'll go deep into subnet masking. But if you sit here, again, we're looking at this configuration panel, right? We have the IP address. And so the IP address is what actually identifies your computer on the network. And then under that, we have something called the subnet mask. And so when we look at an IP address, there's actually two things in the IP address. You have the identifier for your computer or your device, right? So the server, the printer, whatever else. And you actually have the network identifier too. So your IP address has both the network identifier, this is the network that we're on, and it has the actual computer identifier, the computer that you're looking for. What the subnet mask does is it shows you where to split the IP address so you know what is the computer identifier and what is the network identifier. What we have here is something called a Class C subnet mask, which we'll get into later when I've had more coffee. But basically, this is a very standard subnet mask. You see 255.255.255.0. What this means when you see the 255 here is that basically where the 255s end, that's what shows you what is the network identifier and what part of the IP address is the computer identifier. So this is computer 199 on the 192.168.1 network, right? So if you were trying to ping 192.168.2.1 or whatever, this is on a different network. Again, remember when we talk about IP addresses and all that kind of thing, the IP address scheme is all about dividing networks, right? So this is one LAN, then we have a different LAN over here, and we have a different LAN over here, and we have the internet over there, right? So when we talk about the network identifier of the IP address, basically what we're trying to say is what is in our LAN, what is supposed to be the peers that we're supposed to be communicating with. If a computer is in a different network, right, then you need a router in between to be able to route that TCP IP traffic from the one network over to the other network. So when we're taking a look at this here, right, so 192.168.1.199, basically what we know is 192.168.1.1 all the way up to 192.168.1.254, all of these computers are on the 192.168.1 network. They should be able to communicate with each other appropriately, as long as you don't have firewall rules or something like that set up. And so what the subnet mask does is it simply tells you where does the network identifier end for the IP address and where does the computer identifier begin, right? So if we go down, when we sketch something out, so let's say theoretically 192.168. This would not work. Let me be clear here. What I'm about to show you shouldn't route properly, but it's just a simple thing to show you. So let's see, 192.168.1.10, right? So if I had a 255.255.0.0 subnet, basically what that would mean is this would be the 192.168 network, and then the computer would be identified as 1.10. So if you had another computer that's 192.168.2.11, that would be on the same network because that's where the subnet mask is dividing it. If you go down, and theoretically, again, this won't route properly, but I'm just trying to give you a simple example. 192.168.1.50. Theoretically, if you had a 255.0.0.0 subnet mask, that means this would be the 192 network, and the rest of this would be the identifier for the computer. Now, to be clear, again, we're going to have to do a class. We're going to have to do a class on octets. If you're like, but Eli, what about the octets? And what about 1, 2, 4, 8, 16, 32, 64, 128? Where does that come in? That comes in at the next class. The most important thing I just want you to understand right now when we start talking about this, the subnet mask, is all the subnet mask does is when you're looking at that IP address, it shows you what portion of the IP address is the network identifier and what portion of the address is the computer identifier. And for the rest of this, we will have its own brutal hour-long class to explain that. So now we know what the IP address is, right? So the IP address is the address of your computer or device on the network. Your subnet mask then basically tells you where the network identifier component is and where the computer identifier component is within that IP address. When we come down and we look at the configurations, the next configuration we're going to take a look at is the default gateway. And so it's really important that your default gateway is configured properly whenever you're dealing with TCP IP4, because basically what the default gateway is this is your router. So what a router does is a router routes communication between two different or multiple different networks, right? So if we're sitting here, and again, we're on a TCP IP network, and so we have our LAN here, and let's say it's 192.168.1.x. So this is how we talk about networks. So this LAN is a 192.168.1.x network, and if we have a computer that's on this particular network that wants to talk to another computer, and their IP address is like 10.1.10.x, something in that network, then you are going to need a router to route the traffic between the two LANs, right? So this is layer 3. This is where the internet protocol comes in, and this is where we have IP addresses and subnet masks and all of that kind of thing. So the IP address of the default gateway that you plug in, right? So this configuration right here, basically what this is going to tell this particular computer is if you cannot find the IP address you're looking for on your local area network, then go to the router, go to this default gateway, and see if it knows where the hell the IP address is. A big problem that you'll see here is essentially people fat finger this. And again, remember in the technology world, it's either right or wrong, right? If you put 192.168.1.11, and your router is 192.168.1.1, this will not work. If you put 192.167.1.1, it will not work. You have to make sure you put that in correctly. I've seen this with junior level admins. There's something called DHCP. We'll talk about that in a few moments. Basically, that's where you can dynamically assign IP addresses and other network configurations to the devices that connect to your network. And sometimes a problem that will happen is somebody's a little tired, they fat finger things, and they simply plug in the wrong address for the default gateway, and then all of a sudden, none of your computers are able to get out to the internet. None of your computers are able to communicate to anything that is off of their local area network. So all the default gateway is essentially it's the router that gets you off of your local area network. For most people, if you have a home office or if you're dealing with your home or a small business, most of the time this will be whatever the router is for that business, right? If you have your internet modem and you have a router built into that, whatever that IP address is, that is going to be the address of your default gateway. When you get into more complicated enterprise class systems, it might be changed a little bit. But that's all this is. Basically, if you cannot find the computer on the local area network, go to the router, go to the default gateway to see if that IP address is available somewhere else. So now that you know what a default gateway is, let's go down to the primary and secondary DNS server. Microsoft always changes things for whatever reason. They say the preferred DNS server and the alternate DNS server. Generally, we call it normally the primary and the secondary DNS server. Depending on the computer operating system that you're using, you may actually even have more DNS servers. So I like using Mac. That's right, I'm a computer guy that uses a Mac. And with a Mac, you can actually put just a crap ton of DNS servers in there if you really want to. But more or less, when you're dealing with this, if you're going to be taking the test, it's the primary and the secondary DNS server. So what is DNS? Tell me if you've heard this one before. We will have a class on it in the future. So to understand what I'm talking about right now, you need to go into the future and take the class that I haven't yet created and then go back and watch this. Anyways, again, trying to flesh this out as we go. What DNS server is, what a DNS does, is basically this resolves what are called FQDNs, fully qualified domain names, to IP addresses, right? So we talk about a fully qualified domain name. Layman's terms, keep it simple. Keep it simple for where we're at right now. Essentially, this is a human readable, a human rememberable name that you will use whenever you're trying to access a server that the computer system, DNS, Domain Name Services, will then resolve to an IP address. Again, right, an important thing to understand with this whole networking communication thing is there's a whole bunch of resolutions going on. Basically, there's a whole bunch of I understand something that what I'm interacting with doesn't, so we have to come to something that what I'm talking to will understand. That thing is then going to try to talk to something else that also doesn't really speak what it needs, and so there has to be a resolve, right? So we use ARP, Address Resolution Protocol, to resolve IP addresses to MAC addresses. Switches use MAC addresses, they don't use IP addresses, and so we're going to need to turn the IP address into a MAC address so that the switch knows what the hell to do with it, right? Basically, when we're talking about DNS, we're talking about fully qualified domain names, this is taking something like CNN.com, right? Like you do not want to have to remember the IP address of every web server that you're going to want to go to, right? Like, again, CNN, YouTube. I mean, can you imagine if you had to remember what YouTube's IP address was and you had to remember what CNN's IP address was and Breitbart, I'll throw Breitbart in there too, Breitbart's IP address. Like imagine like if you had to go to Reddit, imagine if you had to remember IP addresses for everything. Like the bad old days when I was young and we had to remember everybody's telephone number, right? It's much easier just to go to your smartphone and click the name you want and go to that person, right? And essentially that's what DNS does, right? So what DNS will do is it will resolve that fully qualified domain name to an IP address, and then once your computer knows the IP address, then however the routing goes in your network, it will then connect your computer to the server that you're trying to communicate with. So what DNS does is it takes, again, CNN.com or mail server, so you have local host name within your network, so you may have an Active Directory server. That might just be called server, if you're like complicated like me. Server. Or you might have mail server, or you might call it Jupiter or Saturn, right? There's naming conventions. When you go into your infrastructure, the servers in your infrastructure may have naming conventions. They may be named after, planets in the solar system. They may be named after apparently a Harry Potter. I was just talking to somebody. I was having a beer the other day with somebody who works at a pretty prestigious place. And apparently they had like this really big Harry Potter fan like 8 years ago. So all their servers are named based off of Harry Potter characters. Anyways, right, you're going to go in there. Those are all the local host names, basically the computer or the server names. And so when you're plugging information in order to connect to your Exchange server, or you're trying to connect to your Active Directory server or whatever else, you're going to plug in whatever that server name is. That gets resolved to an IP address, and then your computer actually knows who to communicate with. So when we're looking at the IP address configuration here, we get this preferred DNS server and this alternate DNS server. Basically what this says is go to this DNS server first. Go to the primary first. If the domain name or the fully qualified domain name resolves to an IP address, the first place you go, then take that and use that IP address. If for some reason this is not accessible, you don't get a resolution back, then go to the secondary or the alternate DNS server and see if that server has what you're looking for. So this might be used in the normal world with DNS servers, where your primary DNS server might be a DNS server that's up in the cloud. So 8.8.8.8, this DNS server right here is actually Google's DNS server. So if you want to make your network fast or whatever, then you're going to try to have all of your computers resolved to 8.8.8.8. So when they're trying to go to CNN.com or Breitbart.com or Reddit or LinkedIn or whatever else, the 8.8.8.8 will give the IP address for the websites that they're trying to go to. But with DNS servers, and we'll get into this in the actual DNS class, this DNS server that is in the outside world has no idea what your internal network looks like. It doesn't know that the local server is called Server or Jupiter or Hogwarts or whatever else. Whatever the naming convention is within your local area network, this external DNS server has no idea what the names are internally. And so you might configure your secondary DNS server to be the DNS server for inside your network. So maybe 192.168.1.1. So many times your router and your server and a whole bunch of stuff will be the same IP address. So what you might do here is your secondary DNS server, you might have that be a local internal DNS server. So if you're trying to get to server or mail server or whatever else, you'll go to the primary DNS server that is outside your network. What is outside your network doesn't know what's going on inside your network. It will not resolve properly. So then your computer will go to the secondary DNS server, which will be 192.168.1.1. This will know what's going on in your internal network, and then it will resolve for the mail server or whatever else that it's trying to get to. So again, when you're doing these primary and these secondary DNS servers, most of the time this is the kind of configuration that you'll just kind of be given, right? So if you're dealing with your router, right, the modem, the router that your ISP gives you, many times they will tell you what DNS servers to use. So they'll say, plug in, this is your primary, plug in, this is your secondary. If you're on an internal network, your administrator will most likely give you what is supposed to be your primary and what is supposed to be your secondary. So most of the time, as like an average user, you will just simply be given this information, or it'll already be plugged in for you. Where it gets interesting and complicated is once you're a technology professional and you're actually building out your network, trying to optimize it more, then you can get into some interesting configurations here. But all this does is the DNS server maps fully qualified domain names, human readable names, to IP addresses, and this is the configuration within your IP address scheme where you actually say where those DNS servers are. So now that you understand a little bit more about IP addresses and subnet masks, default gateways, primary and secondary DNS servers, let's talk about how you can automatically configure the new computers that come onto your network with the appropriate configurations. So whenever you're dealing with IP addresses, basically you can either have a dynamic IP address or a static IP address. And basically what that means is if you have a static IP address, you hard code your IP address to that piece of equipment, and the IP address never changes, right? The IP address that it has should be the IP address that it always has until you actually go in there and you manually reconfigure the IP address. Having static IP addresses are very useful for servers, right? So if you have an Active Directory server, DNS server, all the kinds of server services that you're going to use, generally on your network, you're just going to have a static IP address, and basically it is just always going to have its IP address. But what about all the other computers that are connecting to your network, right? So if you are dealing with a Class C subnet, again, we'll talk about that more in an additional class, you can have 254 computers connected to your local area network, right? So let's say 192.168.1.1. And let's say you reserve 192.168.1.1 to 192.168.1.1 1.10, you reserve those IP addresses for networking equipment, your router, your wireless access point. You reserve those IP addresses for your servers, that type of thing, right? So let's say you have 10 different computers, 10 different devices, and you're going to statically assign the IP addresses of between 192.168.1 to 192.168.10 for those specific things. At that point, you still have 244 open IP addresses that can be assigned to whoever else comes onto the network. So, imagine, especially in the modern world with like remote work, imagine you have like a co-working facility. And so you have people that come into the building with their laptops and they leave the building with their laptops, right? And you have hundreds of people that come in throughout the day. You do not want to have to statically assign every single person who walks through the door an IP address and have them manually configure all of that information. Again, when you deal with networking problems, 99% of the time, somebody unplugged a network cable. That's a layer 1 problem, the OSI model. The other 1% of the time, somebody fat fingered something and they just typed in the wrong configuration, right? If you have to type in an IP address and you have to type in a subnet mask and you have to type in a default gateway and you have to type in the primary and the secondary DNS servers, somebody is going to screw up all the time, make one of those numbers wrong, and then things are not going to be set up properly. They're not going to be able to communicate on the network. And so that's where we have something called a DHCP server, a dynamic host configuration protocol server. So basically what this does is this dynamically assigns IP addresses and other network communications to all of the computers as they come into your network, right? So you have one person, they connect their computer to the network. Your DHCP server is then going to dynamically assign them an IP address, tell them what the subnet mask is, tell them what the default gateway is, tell them what the DNS servers are, and away they go. They are now on the network, right? The next person comes in, DHCP keeps track of all of these different DHCP addresses, and it will give a different IP address, hopefully same subnet mask, same default gateway, same DNS servers, the whole 9 yards. You have somebody else come in, and basically they are given their own IP address, subnet mask, so on and so forth. Basically, with this process, the DHCP server gives away these IP addresses under a lease scheme. So essentially, one of the things you configure in the DHCP server is you say how long this IP address will remain active. So if you have a network, a normal business network where people don't really bring in their computers and they don't really take the computers away, you may have a very long lease on these IP addresses, right? You may say, hey, you can keep the IP address for a month because it doesn't really matter because the computers don't really change that often. And if that's the case, a DHCP server gives the IP address and it will last for that amount of time. On the other hand, if you have a cyber cafe, you have a co-working space, something like that, and you have lots of people coming in and lots of people going out, then you may want a very short lease because you don't want to run out of IP addresses, right? When the DHCP server assigns the IP address to somebody, it says, okay, that IP address is gone. And then the IP address is assigned to the next person, and then the DHCP server logs that one as being used. And it keeps logging the IP addresses as being used, and if the lease is too long, the DHCP server will think all of its IP addresses are used, and then it runs out of IP addresses, and you start getting what we call quirky problems. So if you have a very short lease, something like 6 hours, after 6 hours is over, more or less, we'll talk about this also in a different class, that lease will expire, and so the DHCP server will then consider that IP address available again, and so it will be able to give it out to the next person. So when you're talking about DHCP, there is the lease length for the IP addresses that it's giving out, and then there's also something called scope. And so this is something that you need to be thinking about if you actually configure a DHCP server, is basically you tell a DHCP server what IP addresses it's allowed to give out. And so you'll say, okay, on this 192.168.1.x network, I want the scope for this DHCP server to be like from 1.10 to 1. I don't know, again, 254, right? So basically what this says is that there are now 244 addresses that are available for this DHCP server to be able to give out to all the computers on the network. One of the issues that you can run into is, what if you have 500 computers that are on the network and they all need their own IP addresses, but the scope that you created only allows for 244 addresses to be given out? That's where we get into subnet masking, which you're going to have a different class on once I've had more caffeine, because subnet masking is brutal. But all you have to really understand here is that the DHCP server dynamically assigns IP addresses. It gives over the subnet mask, it gives over the default gateway, it gives over that DNS information to the computers that connect to the network. And so, you know what? I think we're going to cut this class off right about there. Don't worry, don't worry. There will be more classes on IP addresses and subnet masks and all the stuff that goes into it. But again, one of the issues you run into when you're trying to teach this information is how to give you folks enough information so that you understand what's going on without confusing the matter. And with a lot of these things, at some point it starts to turn into a bit of a mess. So we're going to leave the rest for some different classes going into the future. So the important thing to understand, the takeaways here, the final thoughts here, is remember when you're dealing with TCP/IP version 4, this is a protocol suite. This is the language that is used on top of the Ethernet technology. Again, there are different protocols out there, although you're probably not going to use them, but for the test, you do need to know that. Beyond the TCP/IP version 4 protocol suite, you then have protocols that are built on top of TCP/IP version 4. FTP, SNMP, STMP, RMTP, I don't know, throwing a whole bunch of letters, right? Basically, these are specific protocols that complete specific tasks on the network. If you're trying to send an email, you need a simple mail transfer protocol. If you're going to be watching a video file, you need a real-time media protocol. If you're going to do a voice over IP call, you need SIP, right? Basically, these are protocols that are built on top of TCP/IP, and they require what is called a TCP port. Right? So when we talk about the TCP port, again, essentially think of the IP address as the address to a house, and then the TCP port, or a building, the TCP port is to a specific suite number within that building. If you're going to go to legal firm, that'll be at room 40, right? If you're going to be dealing with HTTP, that will be at port 80, right? When we take a look at the actual IP addresses, again, you have the IP address 192.168.1.1. That's the address for the computer, the identifier for the computer, and it also has the network identifier in there. The subnet mask is what tells you what part of the IP address is the network part and what part of the IP address is the actual identifier for the computer. Under that, we have the default gateway. That is the router that gets you out of the network. If you're trying to find a computer that's not on your local area network, basically your computer will look on your local area network, see if it's available. If it's not available, it will then shoot the communication out the router and see if it can find the computer on the other side of that. You then have the DNS servers. Again, DNS servers resolve fully qualified domain names, human readable names essentially, to IP addresses. You have the primary and you have the secondary. Essentially, if the primary doesn't resolve a fully qualified domain name to an IP address, then your computer will go to the secondary. If it doesn't resolve in the secondary, then it fails out completely. How you do the whole primary secondary thing is an art form unto itself, and as I've said before, we'll talk about it into a different class. We talked about DHCP, and again with DHCP, Dynamic Host Configuration Protocol. What this does is it allows you to dynamically assign IP addresses to the devices that connect to your network. When the addresses are assigned, there's a lease term, so how long the lease is for that particular IP address. If you're in a pretty static environment where things don't change very often, you may want a long lease. If you're in a place like a co-working facility or a cyber cafe, you might want a really short lease. Beyond that, there is then the scope, essentially what addresses are available to assign to the people coming in, and that's what you get with DHCP. Do remember, again, I talked about this with the TCP/IP version 4, that this is a suite. So we have we have TCP, transmission control protocol. That's what does the three-way handshake. That's what does the windowing. Basically, once the computers have found each other, that's what takes over a lot of the communication between the two computers. Under that, you have the internet protocol. That's what actually allows you to have IP addresses and subnet masks, have routers, all that kind of thing. Then we have ARP, again, address resolution protocol. That resolves IP addresses to MAC addresses. Switches do not understand IP addresses. But then under that, the takeaway is don't turn off ICMP. I've seen this, right? Everybody wants to be a cybersecurity expert nowadays. Well, hackers can't hack what they can't see. You know who also can't do work if they can't see things? You. If you turn off ICMP on your network, you're not going to be able to do simple tasks such as ping, right? This is the communication protocol, basically that allows you to do like little basic testing or whatever to see if devices are on your network. Again, this allows you to do a simple ping command. This allows you to do trace route. And let me oh my golly, it is a miserable day. It is a miserable day when you have to do network troubleshooting and you can't ping anything. So unless you know what you're doing, please don't screw with ICMP. And then you have IGMP, right? Oh, what's the name of that? Internet Group Management Protocol. That's what allows you to do multicasting. This is kind of one of those things that just kind of happens in the background when your computer has to talk to multiple computers at once. Again, it sends out a broadcast, again, to find out like a MAC address or something like that. That's going to use IGMP. Again, be very careful with ICMP or IGMP. I see a lot of folks right now, they get a little cybersecurity crazy. And then they make the senior level admins' lives hell. So anyways, that's the basics. That's the basics of TCP/IP right there. We are truly going to have more class. There is going to be a whole hour-long class or whatever it's going to be simply on subnet masking. Look, if I've got to create the class, you got to watch it. Anyways, we're going to have a class on subnet masking. We are going to have a full class on DNS. We're going to have a full class on some of these other subjects there. So, as said before, if you're still like a little confused, again, like, and this is what I really want to show you now that we're like 5 classes into the series, is that this is what I'm trying to say, is like there's so much. In order to understand one thing, you have to understand something that you haven't learned yet. So again, just so we're clear, it's as frustrating trying to figure out how to teach this sometimes as it is for you to learn. So if you get confused, again, either rewatch old videos or go out onto the internet, do some of your own research. This is very much one of those things where the last class I do in this series, I'm going to say something that makes something in the first class make sense. And that's just what you're dealing with when you're new into this industry. It's just, yeah, welcome to being a technology professional. Anyways, as always, I enjoyed doing this class and I look forward to seeing you in the next one.